his seminar in the climate seminar series. How many first-timers do we have here? So the word's still getting out there. Still have some people coming in, checking things out. Thanks to all of you repeat customers for the seminar series. Climate change, coast and ocean.
Well, good afternoon, everybody. Just afternoon. And thanks, Terry. Probably should just say up front that I've been a little fever this week, so if I mess up, that's why. No, if I start coughing or anything, please just excuse me, and if you talk to me after, don't get too close. So the seminar series is about climate change, and that's fine, but that's a huge topic. And really what we're trying to do is look at California, and that's a real challenge, because we only really understand climate change at the large scale at this stage. But we're getting there. But then even when you get to California, there's so many different environments and sectors. So I said, sure, I'll do coast and ocean. But of course, as soon as you start on it, I could spend my whole life trying to even just make a talk on it. There's so much happening. We haven't got the answers yet, but this is going to be a brief, what I call a brief introduction to it. Initially, I'm going to just do a bit of an overview of climate change, particularly relating to coast and ocean. And there'll be some repeat with previous lectures. And secondly, I really want to focus on two aspects of climate change and the marine realm. One of them, which gets most of the attention, is where climate change is directly affecting human habitation. Sea level rise and erosion, flooding and inundation of the coast, etc. The other is the whole ocean is changing. And with it, all the ecosystem services that it provides to us. So if you think about upwelling and fisheries, or you think about that most of our waste runs off to the ocean and gets taken away and processed in some way. Those are all also threatened by climate change. They're getting less attention in the short term, but they're perhaps more profound on a larger scale. And I'll largely make a few recommendations. So we all hopefully have either peeped at the IPCC report or seen graphs from it. So really the starting point is the couple of key variables, the key phenomena which are happening is getting warmer, sea levels rising, precipitation's changing. In this case, it's snow cover shown up here. It's global, it's climate, and and very much abiotic variables. Actually, mostly physical. But not only that, not only the previous one was we have observed change, but we expect change to continue. So the modeling scenarios going off to 2100, which particularly when you start getting into well, pretty much any phenomenon, but even more so ecological, we can't really have much confidence beyond that. They probably go up, but when we start looking at the ocean, this is the heat content in the upper 700 meters of the ocean, and also from IPCC. And much of the heat that's been coming into the Earth system is contained in the ocean. So that's nice in a way; it sucks it up. But of course, it changes the ocean at the same time. One of the key things that happens is the steric effect, that water expands when it warms up. So this is just a simple demonstration of that, well, not so simple actually, but where the IPCC juxtaposed satellite altimetry, where you measure the height of the sea level from a satellite, very fixed location in orbit around the Earth. It's quite amazing, and you can measure, tiny differences of centimeters or even millimeters. So over 10 years, you get a very nice map of where the sea level has risen and fallen. And at the same time, you can collate data on the temperature of the ocean, like I just showed in that previous picture, in the surface waters or the upper ocean. And you can estimate how much things should expand by. Well, and it's pretty nice because they agree with each other, at least maybe not in exact ways, but in the basic pattern, and roughly the same order of magnitude. And we see that the numbers that you might be familiar with of, the yellows are about 2 millimeters per year. Little pointer somewhere, I'll just so they're looking at sea level, and we really saw pretty much the same data before, but this is probably the biggest single effect on the ocean that we're going to have to deal with in the near future. The sea level has risen, and we're seeing a graph here running from 1880 to 1900 and on to 2000. Observed sea level, big uncertainty back there, getting better as you get into gauges and into satellite data that last 10 years up here. Clear rise in sea level, maybe 15 to 20 centimeters over the last century. Again, all of this material from the IPCC, and there's much more there to read about the details of these data. And then likewise, it doesn't stop there. So the previous data you saw is the instrumental record, and going back into the 19th century, making some estimates. But here you are in the early part of the 21st century, and what are the projections for the future? This is only for one scenario, the A1B scenario. But to look at another 20 or 50 centimeters by 2100. The order of magnitude a meter, 2-3 feet of sea level rise. Yeah, people quite often say to me, well, it doesn't really matter too much, does it? And yet it does matter hugely. So what is the sea level rise due to? And the first contribution I've already pointed out is the thermal expansion. So what we have here is another IPCC graph where they've looked at the different contributions to sea level rise. Here's a zero line. We just look at 4 different contributions, where the blue is from the period of 1961 to 2003, and the brown is from 1993 to 2003, where we have improved data, and perhaps things are going faster as well. They are. So 2 different periods. This is the thermal expansion idea, that as seawater gets warm, it expands, and it, at least in the last decade, has had the biggest effect, about 1.5 millimeters per year. Then you have glaciers and ice caps melting, giving you maybe about 0.5 millimeter a year. Greenland, much smaller. Antarctica, at this stage, quite small as well. You add those up and you get, from the contributions, you might expect in the last 10 years to have a value of 2.5 to 3 with an uncertainty associated with it. And observations, maybe more like 3, a little bit bigger than that. So there's a difference between observations and the and what you expect is a message from Christopher here. So anyway, so there's a small difference there, and I'm not going to go into that. But everything's okay with Eileen anyway. So that key point is the thermal expansion, the steric effect. But the melting is significant as well, and a lot of future potential in that. So that is sort of a very rough beginning of what you might read in IPCC. I figured, I don't know if this is a very good schematic, but I had to do it in any case to tell you how I think about things, or how I think we should all think about them. Is that we have a number of different things going on. I mean, the one is, when you talk about climate change, I always have to stop people and say, well, what are you thinking about? Because there's the emission of greenhouse gases. The Assembly's passed a bill on that, and that's great. But there are a number of other aspects to the problem. My words here a little bit. Anyway, the greenhouse gases are heating the Earth, so you're getting a global climate change in the atmosphere, and that in turn is impacting the ocean, and this is of course a coupled system. But then what we're really working towards, this is all global, and that's all well and good. We know there's a problem, but what does it mean for us, or what does it mean for California, or even what does it mean for the United States? Just starting to get down to this regional change, this downscaling from atmospheric and oceanic change to what's happening in our region. And then you can say, what's the impact on California coast and ocean? And some of the impact is sort of systemic, is due to the whole system, and some is very local. If the wind changes in your backyard, well, then your backyard has a different climate. And if your next door neighbor has a different wind, they have a different climate to have their barbecue in. That's a very local problem, right? It doesn't matter how things are linked, but some others are much more systemic. So there are a variety of ways this downscales. And then there's once you start seeing impact is when you start seeing feedback through the human responses, whether it be policy or behavior. We try to get ahead of the game a little bit, but I think once people start feeling this and seeing this, which is where we are now, you'll start seeing some more feedback. A lot of these feedbacks are not very good. For example, if there's less water, then the humans will probably take more of it, and there'll be even less water for the ecosystem. And so you'll sort of get into a bit of a spiral here. And then, of course, there's, I call it a slower feedback, as we've seen with bills now to control emissions. But that's going to take 100 years or whatever the commitment time period is before it affects things. So while we start off with, this is the Keeling curve of CO2 increase. And here the global climate, let's go back up for a moment. The change in the ocean, what have got things like the meridional overturning circulation or the conveyor belt circulation, things like sea level rise, warming, CO2 levels, are very much all coupled together. Oceanographers have primarily been studying this coupling of atmosphere and ocean, large-scale oceanographers. And really, until recently, I haven't personally been that involved because I'm more interested in the coastal ocean and the shoreline. And but now as you start seeing impacts, it starts becoming very interesting. And this is really what I want to talk about today, the impacts of, much more than the causes of. And so I put a few other words up there to say that I'm not going to talk about them today. We're working on a white paper for the Energy Commission on wave energy, for example. That has potentially a significant role in reducing emissions, or tide energy. And that's a very much a California ocean and coast issue. But I'm going to try and focus on the impacts. Carbon sequestration. I'm not a fan of it, but that's not really a scientific statement because I haven't been deeply involved in the study of it. But the idea that we can get the oceans to suck up more carbon by creating higher productivity. It's quite a, what's the word? Seductive idea because the oceans could suck up a huge amount of carbon. But what's the impact of it? I'm not sure. Anyway, so there's this, the emissions which bring about the climate change and then the downscaling to understand what's going to happen locally. And probably the other box I should have put in here was local changes in human activity. There's a huge amount of environmental change going on, but nothing to do with systemic climate change. It's got to do all with what's happening here in our region. So, for example, if the river flows weaker than it used to, that's not due to climate change in this sense. It's a more of a local environment change. And those two come together very strongly to create an impact, a cumulative impact, not always in the positive sense. Or depends how you think of positive. Often it is in the positive sense, which is pretty negative in terms of impact. Okay, so if we look at California, then we actually do know quite a bit. For example, in San Francisco, we've been measuring sea level since 1850 or so, and this is starting to, this somewhat I'm going to talk about here overlaps with the lecture that Jeff Mount gave on the Delta and with various other lectures. But we know how sea level has risen in San Francisco. It's pretty close to the global average, 2 centimeters per year or 20 centimeters in a century. And although there are lots of debate and details that can mess you up here, it's pretty convincing, at least since 1900, that that the sea level has been rising quite clearly. And likewise in San Diego, tide gauge went in 1905, another sea level rise at much the same rate. In the NOAA site, they have more data and more plots from all the long-term tide stations along the coast, San Diego and Los Angeles and Orange County and right up into Alaska and so on. And I'm not sure if you can see this very well, but they've got here colors showing millimeters per year trends. 0 to 3 is sort of where San Francisco and Global and San Diego are the green ones. You'll see much, actually, if you look even everywhere, much of the dots are green, which basically means the sea level is rising as you would expect globally. But then there are other places where it's red, where it's rising faster. And for that, we go out of California, go to Louisiana, and you know why that is. It's because of the subsidence of the delta. And if we had data in some other locations in California, we might see that. But there are also places like Crescent City, which are quite interesting, where the sea level is not rising. If anything, it's dropping off a little bit, which is much more of a local tectonic. I put the comment in here, didn't I? Tectonic effects of subduction. So that's the local land adjustment or local movement, vertical motion of the land. And if you look further afield, you see in Alaska and elsewhere, here on the Atlantic coast, you see other phenomena due to vertical motion of the land, either upwards or downwards. This plot then is really the same data going from San Diego, and I can't even read it, up to about here, which is about Crescent City is one of these zeros. But many of them, you can see them up there at about 2 millimeters per year. That's the sea level, but we also know something about sea surface temperature in not only globally but locally. So there are these are data from 1800 or 1900, 1880 through to 2000, showing variations in temperature, again put together from a variety of different sources, and showing variations of global temperature, sea surface temperature. So sea surface temperature is, like it says, sea surface temperature. It's not down to 700 meters or anything. And a lot of the more recent data is from satellites or from instruments moored near the surface. And you can see, I really just put this up, I'm not going to go into it in detail. You can see some things which are fairly common, like the Pacific and the global are quite similar. Pacific is a big ocean, North Pacific, the South Pacific. And here's a local one, this is Monterey Bay, and some of the earlier data is more constructed than real, but you can see some of the cool period and the warm period and things like that. But as you start looking at more local data, you can see some of these big fluctuations, which you see elsewhere in the world as well, in Peru and Chile, even in South Africa here, you can see fluctuations, and you can see the links between them. So there are oscillations, the Pacific Decadal Oscillation, which really is a name given to an EOF, given to a statistical analysis. I don't think anybody's fully explained why it is, and it's mostly for the North Pacific. So some of this variations, long sort of decadal variation you're seeing in the Pacific. With the ENSO, El Nino Southern Oscillation is much more of a global phenomena. And when you're seeing features around the world at the same time, that's some of what you're seeing. So I'm just jumping through a few different things showing more regional scale phenomena, like the sea level, this is temperature, and this is CO2. So we expect CO2 to be rising, and it is, and globally again there's data, but there are 3 stations, one in Europe, one in Hawaii, and one in Bermuda. Hawaii is this one here, and you can see the pH or the PCO2 going up and the pH going down. So the ocean pH has been dropping from about 8.15 to about 8.05, which is 0.1 change in pH. Remember, pH is a log scale, so it's significant change in hydrogen ions, 30% or something like that, and becoming a significant issue of great concern, because there are a number of organisms in the ocean which have calcium carbonate, either skeletons or shells, or so even some of the phytoplankton, like diatoms, which are the base of the food chain. They're really the grass of the meadows, if you like. But the corals, of course, and also a lot of the organisms that live in the seashore with seashells. So this is something which is going on. It's not stopping here. It's projected to go down 7.65 century from now, which is very disconcerting. It can completely disrupt the food chain. And California is ahead of the game on this a bit, because we have upwelled water, which is very rich in CO2. And so both in Monterey Bay and also out of Bodega, a number of studies going on to try and figure out what does it mean and which populations are most susceptible. Again, cumulative impacts, and I can make these little side comments. So if you're a shellfish living on the shore and the waves increased and your shell got weak at the same time, well, it wouldn't be very long before you don't survive any longer. Okay, so that's sort of the overview, giving you an idea of some of the things happening in the ocean. What are the impacts for California? As I said in the beginning, there are 2 different impacts I wanted to talk about. First was, and again, very brief, it's almost frustratingly not getting into detail. Although I have to admit, some of that is, I had hoped to get into a bit more detail, and fever kept me from preparing quite as much detail as I wanted to. But if you think about, if you think about the change in the ocean and where the humans interact with the ocean, it's on the shoreline, it's on the estuaries, and actually increasingly so also in the surf zone where people go swimming and frolicking and water contact and so on. So if you think about that, there are a number then of of phenomena, and we can break this down into many more. The first one I call inundation, whether it's due to erosion of the shoreline or just plain old water rising and flowing over it. But it's a loss, sort of more of a permanent loss of land, and of course a loss of infrastructure, and also of ecosystems or change in ecosystems. The second one are flooding events. We're talking here more about events that happen and the land will get flooded and it might go back down again. Like the tsunami in the Indian Ocean, or like the Hurricane Katrina in New Orleans or something. These are events, and we can expect the intensity and frequency to change. If your sea level rises, the frequency will increase. So this is going to damage infrastructure and ecosystems, and also hazards, because they're short-term events. They're more, if the water level just rose nice and slowly, it's not going to, you can prepare for it, but if it comes in these flooding events, and that's really a hazard and a risk to human safety. And a lot of what is discussed for the delta is related to both of these effects. It's that you could have catastrophic break in a levee, and an island could flood. So people living in that island would have the hazard. But not only that, the freshwater pumps would suddenly be pumping salt water, etc. And if you didn't hear that lecture, it's worth definitely going to the website and that. But then the inundations, well, I'm going to talk a little bit more about these things. Salinity intrusion is if the water level rises, sea level rise, but a variety of other things, then of course the seawater is going to push further inland. That can affect water supply, but also coastal agriculture. And this is more of an East Coast phenomena, but there are a few places here. Low-lying coastal agriculture, and just a small rise in sea level can quite an infiltration into aquifers. And infrastructure, put for example sewers here. As far as I understand the problem, it's quite significant for San Francisco, because wastewater is meant to run downhill towards the ocean. If the ocean comes up a little bit, maybe it's not going to be running downhill so well. It's seawater coming into that's not a simple job to change for any city. Those are three of the classics. But coastal water quality is an issue as well, and particularly in Southern California, where again, it's been a state priority, the Clean Beach Initiative, and a fair amount of proposition money, bond money has gone towards trying to make our beaches healthier. But as the climate changes, very likely that scenario could change a bit as well. And then finally, coastal climate, the idea that where I live near Bodega Bay, it's very cool and temperate, and we can grow Pinot Noir grapes, which is lovely. And I don't have an air conditioner in my house. Fog and sea breeze are important things which can change quite radically. So the perhaps inundation, the sort of nice dramatic pictures what the BCDC prepared, and probably a lot of you have seen this. I think it got into a number of the newspapers. Very static GIS problem, just saying, what's the level of the land, and if the sea level rose by 1 meter, how far would it go? Of course, it's not that simple. It takes a century to do that. Humans respond, and also the biophysical system responds. Sediment moves around, etc. But here, if you look at San Francisco Bay, Central and South Bay, what they did is they plotted turquoise where basically where the 1 meter contour is. And you can see lots of the salt ponds down here getting flooded. You can also see a lot of Oakland Airport getting flooded, and in Richardson Bay, lots of different areas. Here's the Oakland Airport story. Pretty much the whole airport would get flooded. And then this is the Petaluma marshes at the mouth of the Petaluma Slough, where a lot of marshland, some of the only remaining marshland, exists. I chose both of these examples because of course there are responses and feedbacks. The marshes, the whole question is, well, they are accretion environments. As the water level rises, tides will pump sediment up onto them, and perhaps those marshes will remain just fine. They'll just build up with this. Perhaps nature will take care of it if it's functioning as a fully healthy system. And I chose Oakland Airport because it has so much value to it that maybe it's worth building a little wall around it, like the Dutch do. What the implications of that, I'm not sure. What are the costs of that, I'm not sure, but I know that's quite a big asset. And if it's a 1 meter rise in sea level, it's probably quite a doable thing. Well, we've done it in the Delta already. So, so that's about as far as I'm going to go into the inundation. Other than to sort of point out that, of course, it's a general phenomenon. You heard about the Delta story, but all along the coast of California, you'll get inundation, and every system responds differently. So the tidal wetland idea already discussed. Wetlands, whether you're looking at the wetlands back in Tamales Bay or Bolinas, you might expect them to build up. In actual fact, this is quite a nice example in Bolinas because the 1906 earthquake really reset the whole lagoon, and that's the sort of understanding that I think it's the majority understanding, let me call it now, of what's happening at the mouth of Bolinas. The idea that it might be, people are worried it's going to close because it seems to be sedimenting in and so on. And I think the general understanding now is that it reset in 1906, and it's sort of got back to, well, I don't know if you want to call it equilibrium, but to more of a, let's call it equilibrium condition. The open coasts and cliffs, that's a bit more of a, I mean, that's an ongoing problem already because we are on a retreating or eroding coastline, and that's the case just north of us, Bodega Bay. They're at banking on the area. Then there are houses which are now in the ocean because the cliffs have been eroded, and likewise in Pacifica and Ocean Beach and down in San Diego. And it's sort of an unstoppable issue. The question is, how do we deal with it? And a sea level rise is going to be, it's only going to aggravate that. So where places like this in the National Park and Drake's Bay, just north of San Francisco, these cliffs will continue to erode as they've always done, and always be a nice beach here. But if you try and stop this by building seawalls, the beach disappears and it starts to erode, tries to erode more and more, and you pretty much have to have a seawall everywhere along the whole cliff to stop it from going back. So it's a little bit it's a little bit of a folly to try it unless you're really going to go all out and completely armor the shoreline. And then beaches and the beaches not backed by cliffs, and it's a whole different story. And again, that's largely an East Coast problem, but a number of places we have that where the barrier islands. This is sort of like a barrier island, a sand spit here at the mouth of Bolinas. Will get overwashed, and the Maldives Islands, in places like that, sediment will get overwashed, and the barrier island will move a little bit. It's less of an issue that we're dealing with here. So a variety of different, I mean, as I say, this, each of these you could write a book about what should or could happen. And then the morphological response, once this, in each of these, is the rising sea level going to lead to erosion or accretion? Or rather, where is it going to erode and where is it going to accrete? And then finally, the human responses. Different words used a bit, but you can so-called protect, you can build a wall, you can buffer, you can create some natural space, because a lot of these natural systems have developed to be coastlines. That's why they are there. Or finally, you can retreat, and you can retreat before it happens or after it happens. Some of the choices lie ahead of us. Flooding events now are different. For example, if you built your castle and suddenly the sea level comes up, in this case only for a few seconds, it's building a sandcastle. But it's sort of the phenomenon that you might expect for a day, that you would have flooding during the El Nino of 1982, and the waves and tides got up, and then it's gone. But your house is flooded and things are destroyed. The ecosystem that is mostly exposed to fresh water, exposed to salt water, the mass die off, etc. So these flooding events are due to changes in sea level. Yes, the general change in sea level, but also winds. If you have the upwelling wind, it drops the sea level maybe 20 centimeters. You have a downwelling wind, like during a storm on the coast here, the sea level might rise up 30 centimeters. They get really strong. The waves in themselves, they actually pump up the sea level, but they also will tend to overtop the structures. Tides vary, the spring neap tides, but also the winter and summer tidal maximum tide. And then ocean circulation also has an effect. So during El Nino, the sea level is, again, 10 or 20 centimeters higher than during La Nina periods. So it's not just the sea level, but it's all of these different variations and different timescales. And the probability of a wave coming up and eroding your castle here is highly increased if your underlying sea level rises. So it's probably, so if you have a typical distribution of sea level, something like this, and there's a shift in it, then what you can see, of course, is where you used to have very seldom have 100-year events. Now you're having them happen very often. In other words, your 100-year event becomes your 10-year event. And we haven't been very good about keeping out of the 100-year flood plain. We've tried to do the 50, and even that hasn't been very good. That's a significant problem. So the next thing then is salinity intrusion. And I think the delta story probably gives a really good understanding what happens, but it's not just the delta. It's every estuary along the coast, whether it's a big one or a small one. You expect seawater to move landward in other estuaries as sea level rises. And it's the house as river flow weakens. So that and is actually pretty important, because that's the one place where there's a strong interplay between climate change and local environment change. Flow to our rivers on the whole is weaker. Also, if again, it's more of a delta issue, but if the snowpack is melting earlier, the summer flow is going to be weaker. If more water is taken out of the rivers in summer for irrigation, it's going to weaken, and that's when you're going to get your maximum salinity. This threatens water supply. Again, you heard about the delta, but the town of Bodega Bay has the same thing. It has some wells in the tiny little Salmon Creek estuary. Estuary is only 1 kilometer long. It's a small little watershed. But if the saline water intrudes, then that little town will have to do the same thing. And it changes habitat. So maybe that is more malleable and might move, but it probably will not. And then, of course, it intrudes into coastal aquifers as well. I was going to get into estuarine circulation, but I think I'll just leave. I'll leave it, but I'll point out, if it's not obvious to you, if this were an estuary, and this is the mouth of the estuary, because salt water is denser than fresh water, it pushes in underneath, pushes right in like this to the null point, which is somewhere around x2, if you know the delta story much. And then the fresh water flows over on top. As it flows over on top, it mixes some of the salty water up, where the salinity might be 0 fresh. By the time it gets to the ocean, it's quite high, and the ocean is about 50. Likewise, the salt water going in mixes fresh water down. So this whole recirculation then is the shape of the ecosystem. And if you disrupt that, not only, so what I'm talking about here is this moving further up to where you got your freshwater wells, or where your freshwater species are living. But not only that, if you change the rate of the sort of circulation, so-called estuarine circulation, you change the whole habitat in which you go from one estuary to another. You find different organisms living there because of different flushing times or different residence times. Coastal water quality. These are just an example here of Imperial Beach. Every popular beach in California now takes water samples every week. Here's the border of Mexico, San Diego Bay, and here's Imperial Beach. And a master's student who worked on this several years ago. And what we have here is from 1996 to 2003, and at different stations, S9 down to S1. S9 is way up near San Diego Bay, and S3 is down in Mexico. And how many, it's the proportion of exceedances, so the standards for fecal indicator bacteria, and how often are those standards exceeded? Well, when it's raining, or when it's not raining but the river is flowing, the river being the Tijuana River, or when there's no rain or no flow. Or when it's raining there in 2003, stations S11 and S5, it was being exceeded about 3/4 of the time. Those are right at the mouth of the river. And same thing in 98, a little bit different in other years. And maybe some story going on here at S3, which is where there's a lot of storm drains coming out of the city of Tijuana. When there's no rain, it's very much focused on the river mouth. Not so much in 96, 97, because there's no flow in that river. So that's the human management, local impact idea going on. And then when it's not raining and there's no river flow, exceedances are very rare, except right down in the south, because there's an open channel discharge of wastewater down here near S1. So this phenomena of land runoff polluting the nearshore, where humans have direct contact, and in actual fact, we're looking at this for otters as well. The southern sea otter population is not rebounded to what it should be, in spite of everything we're doing, and it's understood to be largely due to disease running off the land. Same sort of story. This whole story can change as climate changes, as the river flow changes. The flows can become more concentrated, the dilution to become less, and also the water, and this is a little bit of an anthropocentric idea, but if the water flows off strongly, it'll be pushed out here, and we don't have to worry about it. Flows weakly, it sort of just dribbles along the coastline for a long way. So we saw impacts of the river, up 2-3 kilometers. Seen similar things in Orange County, Huntington Beach, and in beaches in South Africa. And then lastly, the direct effects is this coastal climate idea. We have a student working on now a little bit. This is an example in July in 2000, last year I think, 2007. Maybe you can't see it so well from there, but you can see the coastline, San Francisco Bay, and you can see this light color. This is the cloud of the marine layer intruding in over coastal California. This is where I live, where it's nice and cool. Great Pinot Noir vineyards here. We never use air conditioners, etc. Often this pushes right in across Napa, and likewise here, pushing up the Salinas Valley, down near San Luis Obispo, etc. Well, what are the dynamics of this, and how are they going to change with climate? There's certain synoptic phenomena where this cool air moves in. It also moves in, follows a couple of routes. It can get over these, if the marine layer is thick enough, it'll get over these barriers here. But if it's not thick, it can still come up through the Golden Gate and up through the Delta and so on, up Salinas Valley, etc. So there's the height of this marine layer and how it interacts with topography, and under what conditions of ocean upwelling and atmospheric circulation would that happen. There's some significant changes in store on that front as well. Impacts, I said here already, on agriculture and energy use, but also on ecosystems and I couldn't think of a better word than human comfort. A lot of people choose to live in coastal climates, not just for the view, but because of the mild climate. So I should actually speed up. I thought I would, surely that's not going to happen. So the impact on human habitation, this is just a really rough idea, just saying, there are a number of things which I've been talking about, erosion and inundation, I should have had there, and flooding and salinity intrusion, water quality and climate. And there are a number of forcing phenomena going on. Sea levels rising, runoff is changing, both due to climate and due to local human activity. Waves are changing, winds changing, water circulation as in the currents in the ocean, air circulation as in the atmospheric flows are all changing. Each of these issues is, is subject to a number of these. So, flooding, sea level, the runoff, and the waves all matter for that. Salinity intrusion, the sea level runoff. So there's a whole lot of possibilities for cumulative impacts, interactions between different things going on. Even the climate thing here, so not only the winds, but also the ocean. I marked those up incorrectly. The inundation is the sea level and the waves. So there's a lot of interacting forcing functions. Second part that I want to talk about is the impact on ocean services. So climate change also impacts ecosystems, and thus impacts the services they provide. So there's this developing paradigm ecosystem-based management. In the marine realm, we just recently had a large workshop on, well, what does it mean and how are we going to do it? Essentially what we need to do is, a healthy, productive, resilient ecosystem is going to continue to provide these services to us. So how do we help to keep it healthy, productive, and resilient? And the services are a variety from provisioning like fish and regulating like the flood control of a salt marsh, to cultural aesthetics of walking on the beach, supporting like the huge amount of photosynthesis that happens in the ocean. We can manage the stresses, we can't manage the ecosystem. And that's really the key, I think. Impacts on the ecosystem are changes in the circulation of water, the currents, the upwelling, the source waters, runoff, sea level, stratification. I'll talk a bit about them. All the different ecosystems might respond in different ways. I'm mostly going to talk about offshore ecosystems because they throw out some of the biggest challenges. Upwelling and stratification are going to change. That can really impact that ecosystem. If you go near shore waters, upwelling, land runoff, stratification, and I should just say the stratification story I'm talking about here is that if the climate is warming, the surface waters are warming, and the deeper waters are cold, so you have a stratification, you have a more of a density difference between the two, makes it more stable and less chance of mixing. And in the ocean, that's critical because all the nutrients are down at the bottom, they're going to get back up again. And your life dies off and it remineralizes, and you have to get it back up again. So the stratification is critical. And initial ideas are that offshore, the stratification is increasing due to warming, and nearshore, the upwelling is increasing due to the increasing winds. So the nearshore is maybe getting more productive and offshore getting less productive. That's just ideas at this stage, and it's a couple of intriguing bits of data. The shoreline ecosystems are things that grow in the rocks and the kelp forests, etc. The waves become very important. The changes in sea level become important. Upwelling is still important. And then in the estuaries, upwelling is still important. Tamales Bay is fueled largely by nutrients that come from the ocean, particularly in the summertime. But the runoff is also critical in estuaries all year, but also in wintertime and sea level. So here I thought I'd just throw it up straight away where, just take a handful of services, and you could probably write about 20 of them, is the ocean provides fish. You can do mariculture in the ocean, so those would be called provisioning services. The shoreline structures prevent flooding. They give you a nice climate. They keep the water quality pretty good, process wastes, keep disease under control. Those would be called regulating services. You have aesthetic and spiritual or cultural services, and then the photosynthesis and the nutrient cycling, supporting services. Now here again, climate change can bring about a change in circulation, upwelling, source waters, runoff, sea level, a whole bunch of different things. And this is, for me, is probably the biggest concern, and is, how is the system going to change? Some of the things we've taken for granted, how are they going to change? So I'll speed up a little bit. We've seen here in the Gulf of Alaska from the 50s to the 80s, significant change in nekton, so this would be little krill, swimming krill, little baby fish, etc. We're seeing a big change in oxygen across the Pacific. So this line here are these data at 200 meters. You see the dark blues, so the oxygen is decreasing, and there's an oxygen minimum in the ocean, and it's rising up and moving north, and that's understood to be the reason why very well these jumbo squid, full-size guy holding a squid, which is as big as he is. But they're no good to eat. I got all excited when they told me they were catching squid that size. You see catches here of Peru. They've faded away, but in Mexico, there's jumbo squid catches coming in, and more recently in Monterey Bay. So there's change going on in the ecosystem, and probably due to that change in the oxygen minimum layer. A good example might be the ocean survival of salmon, which just showing here of, so salmon I probably don't have to tell anybody about as being a key issue. One of the key parts which is poorly understood is what happens when they go out to sea and how many come back. And so looking at ocean survival here, coho salmon, as a percentage is high in some years, 60s, 70s, low in other years. And here's Chinook salmon, which is data of Oregon actually, not California. This is a number in hundreds of thousands coming back. A mean is about 100. High, these are anomalies, high in some years and low in other years. And these relate to this PDO idea I talked about earlier. So the only point I'm trying to make here is that these the salmon survival seems to relate to environmental conditions. And if you look a bit more closely, you see the suites of copepods, northern copepods, which come down during the cold period, and southern copepods, these are tiny little zooplankton species, go north during the warm period. These guys live in cold water and are nice and fat, and so it's a period when the salmon do well. So this is sort of trying to understand ecosystems, but eventually, well, another step here. So you start getting statistical relationships between the copepod biomass anomalies and coho salmon survival with a little bit of statistical confidence to it. Why I'm saying this is, but this is the next step we have to make. If we can understand changes in climate, abiotic changes, how do we understand ecosystem changes? We're not going to be able to model them, but if we can come up with statistical relationships, then maybe we can have some sense of what it's going to do for the ecosystem or for a specific population like salmon. I already said that the ocean is confounded by huge fluctuations or anomalies. This is the temperature in Monterey Bay, and you can see getting warmer and colder through the years from 1989 to 2000. But you can see these the El Nino anomaly here, which is about 2 degrees warmer, quite significant. And likewise, following that anomaly in negative anomaly in chlorophyll, following that a positive anomaly in chlorophyll, and underlying trends. So trying to see the underlying trend in temperature and productivity is awfully difficult, and it's probably going to play out through these different events, El Nino events and EOs, etc. So I've said something about that. So in essence, when we look at impacting ocean surfaces, I think the schematic that we have is that the physical chemical environment is changing. And that's sort of as far as climate change is getting to at this stage, where we have emissions changes in the coupled ocean atmosphere system, downscaling to the California current or whatever. Now you know how's the temperature changed, how's the upwelling changed, how the currents changed. And this in turn is going to affect an ecological community. And it's this community which delivers the services that we value, even though we sometimes don't know that we value them because they've always been there. So this is a very different concept to the first part of impact, which is very much on direct. I can understand it if my house gets flooded. To more like, well, how's all these services the ocean provides going to change? Maybe it's more easier to think about estuaries than offshore ocean. And maybe I don't need to go through this, but there's information in multiple aspects: the transport, productivity, population dynamics, water quality. But there's hope, because here we have other statistical relationships of zooplankton, incorrectly spelled, with a bunch of multivariate indicators of physical environment and some relationship, not strong, but it's there. And here for seabird production, again, 18 variables in this. It's starting to get a relationship. Will these hold under climate change or not is a question, but it's holding through fairly big fluctuations in the climate, the PDO and ENSO. Empirical models rather than dynamical models. I won't go into this in detail. Just annual zooplankton production, phytoplankton production, and this is how strong the upwelling is. Strongest upwelling is not necessarily more productive than weaker upwelling. There's matching in the system. And then I think this is lastly on ocean services that I've been talking about offshore ecosystems and influences of change in the physical environment. Equally important are the coastal nearshore estuarine environments that I haven't talked about. And equally important, which I haven't talked about, that I could fit it in really, was acidification. I mentioned it earlier. It's as severe as any of the temperature going on in the ocean or any of the sea level rise. And the map of how it's changed. And in conclusion, then I've tried to give a brief introduction to a variety of issues, both the direct impact on where we live and the indirect impact on humans through how the ocean ecosystem changes. I haven't really got into the biophysical feedbacks. They're significant, and they make it rather difficult to project what's going to happen. And I've really little mention of the policy and behavior feedbacks at all. So what could or should we do about it? My feeling is that in terms of developing a better policy and in terms of helping humans figure out how to behave better, these downscaling models are forcing. It's happening. The state has made a number of those happen already. We're starting to understand what happens in California in terms of those initial IPCC ideas of temperature and sea level rise and whatever. Yeah. So the question was about explaining the term forcing, and I use it in just a rather loose way here, that in any system, forcing is what you do to it, and then a system will respond in some way. In this case, I'm thinking that when you're looking at the California Ocean, that as the Earth's climate changes and the temperatures, sea level, things like that are going to change in California. And I'm thinking of them as forcing because they will then perturb the system, and the system's going to respond to those changes. I'm calling that forcing. pH would change, and that would be forcing as well then. So the things that sort of you inherit or you receive from elsewhere are going to bring about change. And then likewise, how humans behave in the watershed would be another type of force, bring about a response in the ocean. Hopefully that makes some sense. But it's used loosely, and people use them in different ways. Second thing is to develop scenarios or possible situations. Is a classic that IPCC has used, and a little more difficult when you're looking at complex ecosystems and not just a physical environment, but it's what we have to do. And of course, the focus has to be on high risk or high cost. If something's very likely to happen, we need to act on it, and something is maybe not so likely, but it would be a huge cost, we also need to act on that. So that's, I think, where a lot of tension can happen in the ocean and hasn't happened yet. Thirdly is the cumulative concerns. When do we have two different phenomena which are going to interact and make it doubly worse, or they're going to interact and actually counterbalance each other? We've seen a number of things like that in climate change, likewise in ocean ecosystems. Thirdly, we really need to start getting a quantitative understanding of a system and how it responds. That will use models, but it has to use data as well. If this happens, then that's likely to follow. Those are the statements we need. Or if this happens, then there's a 50% chance that you will get that. Those are the kind of statements we need to develop, and it requires a fairly concerted effort to get there. And then the fifth point is to manage for resiliency is the best way I could express it, which is if you've got a resilient system, because again, what I keep saying about the ocean is it's not a human-dominated system at this stage. The coastline is. The ocean, even a lot of our estuaries, are not totally dominated by humans. They're still functioning as fairly active natural systems. So what we want them to be is resilient, healthy, and productive. Then when things change, they can continue to do a good job. So there are some stresses, some things we're doing to those systems which we do have control over. An example would be polluting the ocean. An example would be catching too many fish or whatever. Those are the things we really need to. We don't want to stress out the ocean too much because we don't know what the climate change stress is. How to be resilient. Best available technologies. A number of these, we can definitely do a much better job on ocean water quality. But to get there is this need to prioritize impacts. These two kind of interact a little bit. I don't think we really have a clear idea. We know about pollutants and contaminants, but we don't really know which ones are doing a number on what part of the ocean. Our work following Clean Water Act has all been in the watershed, which is great. But we need to get a clearer idea of which ones are really hurting the ocean badly and which ones are maybe not hurting as much as we thought they would. And then I sort of come back to precautionary, even on restoration. When you change things, you got to be careful. And so that's not meant to be just precautionary on any development, but just on try and let the system be resilient and healthy. And then finally, spatial management. I haven't expanded on that. But the recognition that some parts of the ocean and coastal ecosystems are very healthy, and we should try and keep them that way, and others are totally human-dominated, and that's maybe okay as well, and we manage them in that way. We have different approaches for different places. And that's all I have to say. Thank you. Wow. Yeah. Right. Yeah. So the question, I'm not going to do justice, is about sucking up CO2 in the ocean, the carbon sequestration idea. And there have been a number of papers, fairly high-profile ones, because on the one hand, let's do what we can, let's be innovative humans, and we could make the oceans more productive. But on the other hand, what's going to be the response of that? And we only have one when you're doing large-scale ocean things, we only have one of them. And then on the third hand, it's not clear that there's a net benefit. There's a local, productivity bloom, and it'll suck up carbon, but you're going to actually take up more in the ocean than you would have overall, and it's not. I think there's not too much to hope, I would say. I mean, we should study it, but save us. Yeah. So more direct human impacts, I think you're talking about, rather than the climate. The changes in the pH are strongly associated with climate. So the more CO2 in the atmosphere, more CO2 in the water, and then there are all these chemical equilibria that go on, and then they release, you get more and more hydrogen ions, and so the pH drops, becomes more acidic. That's entirely part of the CO2 story. There might be local pH changes. I think the EPA has a standard of 0.2 pH change from some ambient background. So we're at 0.1 already due to climate change. We're almost there globally. That's kind of scary. But there's a lot of work happening on disease in the ocean. And as we're starting both in the microbiology, being able to identify the pathogens in the ocean and understand where they're coming from and where they're going to in their survival. I can't tell you too much about it because it's really a fairly new topic. The standard approach has been the idea of fecal indicator bacteria, that you can go to a water body and you can sample and culture the total coliform, fecal coliform, more recently Enterococcus, and if there's more than so many of them there, that indicates that you've probably got some water with fecal wastes in it. Epidemiology is not great, I would say. But it's been pretty effective because it really has helped clean up our waters. It's a paradox. But every city has gone to look around and they found a lot of leaking restrooms, broken pipes, and that's really helped things. But the otter case is quite an interesting one. Because toxoplasma is found in cat feces, and it comes down the rivers, it gets into the coastal ocean, and you can diagnose it in dead otters because it's a colitis, I think, something. Brain disease, whether they die from it or whether they get stupid and the shark bites, and the primary and secondary causes, and it's a significant. Like a quarter of the population are dying from associated, either direct or associated causes. That's don't quote me because I need to check it, but it's significant, something like that. And so it's a very good study of human health because we can really study the otters closely, and they don't get in their cars and drive away at the end of the day. If it helps. Right. 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 The questions about sea level rise and to what extent it's global or local, and to what extent the data is available. It's very much a global phenomenon. As you say, if the tub fills up on this side, it's going to fill up on that side as well. And so I did show some of that right at the beginning, and it's about the same. There's 2 millimeters per year rate worldwide. The data, of course, is varied. There's some old gauges in Europe going back to 1900 or earlier. There are gauges in South America and in Southern Africa and Australia and places like that definitely go back to 1950, probably a bit earlier than that. So yeah, you can see this record in most places. And then more recently, although it's a short time, you get this amazing data from satellites. Well, I showed you 10 years of Topix Poseidon. There's a bit more of that, but not as good a quality. You're getting sea level data at every point on the Earth. You're getting great spatial coverage. And then you get a few of these gauges in, I'm trying to think of the oldest ones, but definitely European gauges go back, I think, to 1800. So yes, it is a worldwide phenomenon. and it's happening everywhere. But the local phenomena changes a bit because the land might move, as in Louisiana, Mississippi Delta, or Bangladesh as well. Land's moving. So, right, this is about the Gulf Stream and that circulation is could stop, which has been written about quite a bit. No, I don't have any personal view on it because I haven't worked on it, but I did hear Wally Broker speak about it a few weeks ago, and I came away with the idea that it's unlikely. It could happen, but it's unlikely. Yeah, sure. that really change everything quite dramatically. Thank you.